Welcome to Module 2. We're going to be looking at the first and second law in this module. So our goals for this module are that by the end of this module you should feel confident that you can solve problems requiring the use of the first and second laws. In particular, I want you to be able to select the appropriate form of the equations based on whether this process is closed or open or transient. And then write a material balance for the system, write an energy balance for the system, and write an entropy balance for the system. Gather data necessary to solve these equations. Okay. So let's look at the three different types, closed, open, and transient. A closed system, the mass balance simply is that the mass at the beginning equals the mass at the end. So that's simple. The first law, energy balance, says that the heat transfer equals work plus the mass times the total energy. And it's U plus kinetic energy plus the potential energy at the end time, time 2, minus the beginning time, time 1. The second law says that M2 times the S2, the entropy at the end of the system, minus the entropy at the beginning of the system, is equal to the heat generated by this control volume divided by the temperature that the heat transfer would have occurred. Now, this is not going to be exactly equal unless it's a reversible system. We'll talk more about that in the next module. So, in order to make them equal, we add a term called entropy generated. Now, entropy generated is not something physical that exists. It's just going to turn this fact that the entropy doesn't balance with the heat transfer and make it so I can write an equation. Entropy generated is always positive. You must get a positive value whenever you do this calculation. So this is the basic forms for the closed systems. If I have an open system where I have flow through and it's at steady state, then there's no change with time. And so what that tells me is that the mass coming in for any streams in or out is going to equal the mass going out of the system. Because of the flow, it turns out that what I need for my total energy has to include the energy for moving the material. So H is U plus PV, and so my first law becomes the one that you see here. The heat transfer is equal to the work plus the total energy using enthalpy out minus in. The second law, again, is this entropy pseudo-balance. Okay, the entropy out minus the entropy in is equal to how much heat transfer occurred divided by the temperature it occurred at, plus, again, to make it an equation, this entropy rate generated. Now, steady state equations are usually done as a time dependent, so per unit time. And so therefore these are all rates in these equations. The final type of system is a transient. Okay, transient systems are, they have characteristics of the closed system and the steady state system, so they are not steady state. Basically, you typically have a system that contains mass and it's leaking, or you have something that was empty or didn't have much mass in it and it's being filled. Okay, so you have some stuff in there at the beginning, some different stuff in there at the end, and you have things flowing in or out. Okay, the mass balance for that says, well, the amount in there at the end minus the amount in there at the beginning, the change of mass inside the system, is going to equal to what came in minus what went out. The energy balance says that Q is equal to W plus, well, now then I have to account for all the total energy of the flow, out minus N, and the total energy of what's contained in the system. The ones that are flowing have H, the ones that are contained and sitting there at the beginning or end time are U. The second law says, well, the total change in energy, or entropy, is the entropy at the end minus the beginning, plus what left minus what came in, so exit minus inlet, and that's equal to the heat transfer over T. and again, plus this entropy generated. Now notice that the way this equation is done is it's not in terms of rate. So I have material flowing through there, and I'm going to account for if I let 1 gallon per minute, okay, happen for 1 minute, then I have 1 gallon that flowed. If I have 1 gallon per minute happen for 2 minutes, then I have a total of 2 gallons. So you're going to have to multiply by the time to get rid of the rate on your flowing streams. It's the mass, not mass flow rate, that came in or out. Now, to do these calculations, we are going to need to estimate changes in both internal energy and enthalpy. And sometimes we have data tables, but not always. And so in those cases, we're going to define the constant volume specific heats. Okay, they can be constant volume or constant pressure specific heats. The constant pressure specific heat is also the one that a lot of times in a chemistry course you learn to call the heat capacity. Now C sub V is du dt at constant volume. We're going to be talking a lot more about this throughout the rest of the course, but for now, it is how the internal energy changes with temperature if I hold the volume constant and change the temperature. C sub P is how enthalpy changes, H, with temperature, holding the pressure constant. Now, if I happen to have a constant volume process, du is Cv dt, and if I happen to have a constant pressure process, then dH is Cp dt. Okay, but I can use this because U and T and H and T are all state properties. They are not dependent on the path. I can use this to make calculations even if I don't happen to have a constant pressure or a constant volume process, if I am willing to make some adaptations. So let's talk about specific cases. So first let's look at ideal gases. Okay, U and H are going to vary with temperature, but they're typically for ideal gases, the change with pressure, actually I can prove it eventually. Okay, it doesn't change with pressure, it only changes with temperature. And so therefore, what happens is that delta U for an ideal gas is exactly equal to the integral of Cv dt. Okay, if I want the total, I multiply by mass. If I want the specific U, I'm going to just leave it Cv dt. Same thing for the enthalpy. Since it only changes with temperature, not with pressure, I only have to integrate this one piece. I don't need to do any further calculations. Now, formulas for C sub P as a function of temperature are in the textbook on page 684. But CV values are not. But fortunately, it's easy enough to calculate C sub V because you can take CP and subtract R using the same units, okay, R and whatever units your C sub P units were, and that will get you an expression for C sub V as a function of T. For solids and liquids, well, okay, what happens is that I end up with a much more complicated expression. If you relate du and dH using H equals U plus PV, dPV, okay, volume doesn't change very much. And so if I'm holding pressure constant, it turns out that dH and du are almost exactly the same. So I can just use Cp dt for both delta H and delta U for solids and liquids. Now the data for C sub P for solids and liquids will be found on page 685. In this textbook, they are a function of temperature. So we're going to look at one example, and we'll do some more of these in the next video, but we'll just do one example for now. So we have an insulated nozzle, okay? So an insulated nozzle, insulated means that there's not going to be any heat transfer. A nozzle is basically just a pipe that narrows, okay? And in that case, there's no moving parts, so there is no work. These also are going to be small, okay? So there's not going to be great changes in height as I go across this nozzle. Okay, some things that I know just from reading just the first three words. It's going to expand air from 500 Kelvin and 1 megapascal to 440 Kelvin and 0.5 megapascal. So the temperature is going to go down and the pressure is going down in this particular case. They say the inlet velocity is small. Now what they're telling me with that is that the inlet velocity is so small that I can ignore it. So I'm going to call the inlet velocity 0. I know it isn't. The stuff was moving. Okay, but I'll call it 0 because it's going to not really affect the problem very much. And then determine the exit velocity. Okay, so velocity is a little different, but remember my balances are going to include dealing with kinetic and potential energy. So here, kinetic energy must be important. Now, if you remember nozzles back in the day, okay, when I think of a nozzle, what I usually think of is when I go out to water my garden. And what I usually do is I stretch the hose as far as it'll get, and then it just won't quite reach the very back corner of my yard. So I typically just shove my thumb in front of the thing and build myself a nozzle, okay? It's just a reduction in the area, and it forces the fluid to go at a higher velocity so that it can reach all the way out to the far corners of the garden. So that's the kind of thing that they're talking about here, maybe a little bit fancier than my thumb. So the first thing I like to always do is figure out, first of all, what type of system is this? Is this a closed system? No flow in or out? Is it a steady state system? Flow that's just consistent from one time to the next, no change over time? Or is it transient where I have things coming in and out, and so I have accumulation, or I have, but I have flow and change with time. So in this case, I've got a steady state system. We just have things going in and going out, no accumulation inside there. So then I need to ask the second question, what are the appropriate forms of the first and second law? Well, we've got the slides earlier. So I know it's steady state, and I know then that means that the first and second law equations are these right here. Okay? So I have this. Mass in equals mass out, so the mass flow rate is going to be the same at the inlet and the outlet. Here I have the first law, heat transfer. Oh wait, it was insulated, so that's 0. Work always requires moving parts. Okay, there are no moving parts here, so that's going to be 0. I have enthalpies at the inlet and the exit. Okay, but I have temperature and pressure, so I'll find data. And I have the velocities at the exit. That's what I'm looking for. Velocity at the inlet, we're calling it 0. And then I have the height at the inlet and exit, which we're saying, oh, a nozzle's small. Couldn't be too much of a height change. Down here on the second law, I have no heat transfer, so this is 0. So I would just simply take the mass times the the entropy at the exit and inlet, and that will tell me how much entropy was generated. Okay, so simplifying those equations, that's what I end up with. I use the fact that mass in equals mass out so that I get these expressions without the mass in there. Okay, so it didn't matter that they did not tell me what the mass flow rate was. And then I go looking up data. Now, velocity squared equals 2 times the change in h. This is air. In the textbook we only have properties for water. Okay? I gave properties for propane. So what are you going to do? Oh yeah, air is one of the things that I said you can usually call an ideal gas. Now this temperature change isn't very large, so I went ahead and just used a constant C sub P. It would be better to integrate from temperature 1 to temperature 2, but yeah, okay, this was a shortcut. I have this. The units are a little crazy. I get velocity squared as 123 kilojoules per kilogram. If I just take the square root right here, I end up with crazy units. Kilojoule per kilogram square root. that's not velocity units. So what I have to do is I need to, before I do the square root, do a unit conversion. So here we go. I've got 1,000 kilograms is a kilojoule per meter square second square. Okay, and so multiplying by 1,000, now I have units that are meters squared per second squared. I can take the square root. I have 350 meters per second. Okay. If I do the second law, and we're going to actually do this in the next module, this is the formula for how to calculate delta S if you only have C sub P, and this is the formula. Save that mentally until after the next module. Alright, so this concludes this video. In the second video, we're just going to work a couple more examples.